In the previous video, we saw that we can write the complex velocity, a general form of that in terms of this Laurent series, in terms of the net flow and the circulation. Turns out that that those two are only related to the very first coefficient in this Laurent series. Actually, the second coefficient, I guess. This is the zeroth coefficient, so z to the 0. And this was z to the first power here. You see that z in the denominator. And then the rest of the series is from 2 to infinity. So anyway, it turns out that that was the only coefficient that was related to the net flow and the circulation. And now what we'd like to do is take this equation for the complex velocity and plug it into our equation for the forces that we get from Blasius. So this is the Blasius relation for the force on this geometry, and now we can, we've got this complex velocity in here, and we know that the forces are related to that. And now we'd like to just plug in this very general form into this and see what we get. Okay, so what we need is a WZ quantity squared, okay, which is pretty involved because we have this whole infinite series here. So we're going to take this equation here and square it basically, and if we do that, we can actually get we can write this as an infinite series from n equals 0 to infinity of b, we're going to call it bn z to the n. Okay, when we do that, we end up with another infinite series that has different coefficients than we had before, because as you square this, you're going to take this term and multiply it by every other term, and then we'll take the second term and multiply it by every other term, and so forth. But when we do that, we're just going to come up with another series, an infinite series of from n equals 0 to infinity, z to the n in the denominator, and we'll have different bn coefficients. We can actually work through and figure out what those coefficients are, and I'll just write down a few of them here. So b0, the first coefficient we get, will be v infinity squared e to the minus I2 alpha. That's a 2 and an alpha. And you can see that really easily. It's just this first term squared, right? That's the first term in our infinite series. And that's the only one that doesn't have something in the denominator, or is related to, that's z to the 0. And so that'll be independent of z. So that's just a constant out front. Then b1 is equal to v infinity e to the minus I alpha times lambda plus I gamma over pi. So that's what we get for the first term, and then b2 we'll get a lambda plus I gamma squared over 4 pi squared plus 2v infinity e to the minus I alpha times a2, whatever our second term is up here in this series, or the a sub 2 term. Okay, so we could keep working through these b3 and b4 and figure out what each of those terms are. Well, it turns out that when we plug this in, so let's just plug in this infinite series over here. So we have a minus in is equal to I 1/2 rho, the integral around the closed surface, and instead of this wz, now we're going to put in wz squared, we'll put in this infinite series here. Okay, so we're going to integrate b sub n over z to the n dz. Okay, so again, this integral, like we did before, we're just going to choose a perfect circle that's large enough to encompass the domain of interest, all right? And that simplifies the math a bit. And so what we get is that z for that circle is going to be re to the I theta, and dz is equal to I r e to the I theta d theta. And so we can plug those in. So the z terms, for example, will go into this z here, and then the dz term will come up here. And so then we'll have this infinite series in terms of, and it will depend on this re to the I theta and I re to the I theta. And it turns out that that a lot of terms cancel again, and all we're left with is actually b sub 1. The only thing we care about is b sub 1 after we work through that infinite series. We'll find out that a minus I n tilde is just equal to negative pi rho times b sub 1. Well, we happen to know what b sub 1 is right over here, so we can just plug that in. And so when we plug that in, we get minus rho v infinity e to the minus I alpha times lambda plus I gamma. Okay, so the pi's canceled there. This pi canceled with that, and everything else basically stayed in there. So we find out that this force, that the axial and normal forces, are related actually to the lambda here, which is our net flow, and gamma, which is our circulation. Okay, let's take this one step further. We could stop there, and that has given us a lot of information, but let's just take this one step further and look at this in terms of lift and drag instead of axial and normal force. So we know that the lift is equal to n, the normal force, times the cosine of alpha, minus the axial force times the sine of alpha. That's just a simple change. You know, if we look at the lift on an airfoil, and so we've got the lift in this direction if the velocity is coming in this direction. Lift is in that direction, drag is there, and then we've got axial force there and normal force there. Okay, so this is just a change, and by the way, this is alpha, this is our angle of attack, so these are those three angles there are alpha. So this is just expressing the lift in terms of normal and axial. We can do the same with drag. The drag is equal to the axial cosine alpha plus the normal times the sine of alpha. Okay, it turns out that we can actually rewrite this in a complex form as drag minus IL is equal to axial minus IN times e to the I alpha. The e to the I alpha gives us the sines and the cosines that we need in here. And so this is just a complex form of this same set of equations here that relates the lift and the drag to the axial and normal. Well, so now let's substitute this in for the axial and normal. Let's just substitute it in here for that axial and normal. And what we'll find is that the drag minus IL is equal to negative rho v infinity lambda plus I gamma. Okay. So so this is the drag and the lift. Instead of axial and normal here, we're now looking at the lift and the drag as a function of these two. And this is a complex number, this is a complex number. If we equate the real components here, we get that drag is equal to negative rho v infinity times lambda, and that lift is equal to rho v infinity times gamma. So this is really important here. Actually, for an incompressible flow that doesn't have blowing or suction and is at steady state, lambda is equal to 0. And so this shows us that drag for an inviscid flow, or any inviscid flow over a two-dimensional surface, will always be 0, as long as there's no blowing or suction. And it also shows us that lift is related to the circulation. So this is the Kutta-Joukowski law here. So this is the Kutta-Joukowski law. And this is the relation between lift, and I should put these tildes up here because these are two-dimensional sectional lift properties. But the lift is related to the circulation, and we've proven that now by using this Blasius equation, or Blasius relation here for the velocity potential related to the forces on this airfoil. And we've taken a very general form of the velocity potential, or excuse me, the complex velocity, and shown that it actually only, that these forces here depend only on the first term, b sub 1. Okay, so that's the only term that matters, and we plugged in b sub 1 and then put that in terms of lift and drag instead of axial and normal, and we're able to prove that drag is equal to 0 and that lift is directly proportional to circulation.